Alright, welcome back guys. In this video here we can discuss further into chapter 3 and um, we're going to talk about measure of relative standing and box plot. In the previous lesson we discussed measure center, which describe the middle value of a data set, and then we look at how we can compare a different data set using the measure variation or the spread of the data. And in this lesson, we look at measure of relative standing, where, like, given a data value, how do we compare the data value with respect to the rest of the data values, relatively where it is in terms of percentage or in terms of z-scores. We're still going to use standard deviation to help with this new concept here, or this new computation of z-score, or just relative standing. That's another word for it. And box plot, another chart that we use to describe difference or compare two data sets as well. So there's a few more things that we need to discuss in this chapter 3. But in addition to measure of variation, we have measure of relative standing. For example, how do we compare the two different exam scores and decide which score is better, and is better relatively in what sense? Okay, so in this case here we have 78 on a psychology exam. Is this score better than a 43 on economics exam? So just from that there, one would say, okay, well, the 78 is better than 43 because 78 is closer to 100 and 43 is not closer to 100. But at the same time, a student can say, well, maybe 43 is better because economics is harder than psychology exam. And that's when I said, well, that's not true. Psychology is harder. So there's no telling that which exam is harder or which exam is better. All we know is the score, but at the same time, are we assuming that 78 here is a good score compared to 43? What if 78 is the score that below the class average, and then 43 on this side here is above the class average? So it's just hard to say that, but there is a way for us to figure out which score is somewhat better relatively to the rest of the class. So to answer this question, so we said to determine which score is better. Okay, we need some more information. We need to see or compare. Okay, how is each score to compare? So I'm just gonna say, I need to see how each score compared to the class average score, or the rest of the class, right? Average score. Okay, so that's what we have to figure out. Now suppose, all right, so this is what we can do. Suppose we given some more information. Suppose the class average score for each exam is given as the following. So we got psychology, okay, exam, and then we have economics exam, okay, and then suppose we're given the mean is 93, and then over here the mean is 53, right? So both are still below the class average, but let's see which score is closest to the class average in the positive way versus not closer. Okay, so the psychology exam, given the mean is 93 points. Let's say also the standard deviation is 11. Okay, and the standard deviations for economic exam is 6. Okay, so what we can do here is we can look at each score. So okay, 78 is It's below the class average. 43 is also below class average compared to the economic exam, but we want to see where they are relatively close to the class average. All right, so let's say we can have the scale like this here. All right, so here is the class average. Let's say here's the mean class average, 93, and then here is the 78. Let's say that's x, 78. Okay, and then on this side we have the class mean is 53, and then the score is 43. Right, so you can see, just judging on the position Y, this score here is a little bit farther to the class average than this one here. But let's find out. Let's see how far that is on average. So to do that, we need to look at the standard deviation. So what we can do is we can compute roughly. Okay, let's take this distance, 93 minus 78. Okay, and then let's divide that by the standard deviation. See how on average how far does 78 score below the mean. Okay, so 93 minus 78, 93 minus 78, we got 15, and 15 divided by 11, 15 divided by 11, so 1.3. Okay, so let's try this around here. Let's try this. Let's do x. Let's do 78 minus 93. That would give us the negative z-score, the negative standard deviation. So that means it's negative. So it's negative 1.36 below the class average. And on this side, 43 minus 53 divided by 6. So we got 10 divided by 6. Negative 10 divided by 6. So that's negative 1.67. Okay. So now, you know what? I showed you an example where the score is 43 is relatively better. So that way we can see that although the score is lower, it can be relatively better. But anyway, it won't matter. In this case here, we got two z-score. We got one is negative 1.36, one is negative 1.67. So we say that the psychology exam score is relatively better, not because it's higher, better because it is okay, 1.36 standard deviation below the mean compared to economic exam 1.67 below the mean. In other words, this score here, this is farther below class average than psychology exam. That's why it's better, not because it's lower or higher. You know, relatively, we want to compare their position to the class average, right? So I could make this up where the score for 3 is better because it's much closer to the class average than the other one. But you guys get the point. So what we just compute there, we call that unit. We call that value is a z-score. It's a standardized value. So what this is a value that represents the number of standard deviations that given x value is above or below the mean. So in other words, we're saying that, hey, here are the data values for this particular set, and we can take any of those data value and we look at where they are relatively to the mean. And when we do that, we look at position Y. We don't associate the original unit of the set. There's no dimensions or there's no unit attached to it. So all we talk about is just positional Y relatively. So which is kind of nice, which allow us to bring two separate data sets, entirely measure two different things, orange and apple, and then just look at where they are relatively for the rest of their data value. So z-score is unitless or no dimension. So z-score. So z-score is dimensionless. Okay, meaning we don't have a dimension, so we just look at position where it is. And the formula is Z equal X minus X bar over S. So this is sample. And then for the population is Z equal capital X minus mu over sigma. So one is population, one is sample. So population, Z-score, and then sample, right? So the scale goes like this here. It goes from 0 to positive 1, 2, 3, 4, so far, and then -1, -2, -3, -4. So this is the standardized Z-score scale. So Z-score. Okay. And then when we take the X, when we convert that to Z, using this formula, the mean is in the middle here. So that's the mean. Mean has Z-score equal to 0. Okay, because if you take the X value that is equal to the mean, and then you compare that to a Z-score, mean minus if X's value is mean minus mean is going to be 0, divided by standard deviation is going to be 0. So Z-score 0 is the mean itself. Okay. From the previous lesson, we had the range rule of thumb. That's how we use to, to identify data values, whether data values are unusual or not. So now we're going to take this range rule of thumb, we're going to rewrite this, and just relabel this in terms of Z-score. Because the Z-score represents the number of standard deviation above or below the mean. Now we can rewrite range rule of thumb using Z-score only, right? So Z-score, standardized value, is the number of standard deviation that is given value X, whether it's above or below the mean. So we can say that usual data values have Z-score, unusual data values have Z-score semicolon. Okay, so we have between, so the data values that are usual have Z-score between -2 to 2, right? Because Z-score represent number of standard deviation below or above the mean, and data values have a Z-score that are unusual. That means the Z-score has to be less than 2 or greater than 2, right? So in other words, we're looking at this here, that range rule of thumb being written as this here. So we have the mean is 0, which is Z equals 0, and then 1, 2, so 2, 1 second, actually 1, 2, -2. So that's the mean there, and that's the mean plus 2 standard deviation there, and that's the mean minus 2 standard deviation. So this is the usual range, and that's the unusual range, right? Okay. All right, so that's just kind of extending what we already know using the new language and new notation, or the new variable. In this case, the variable is Z. Okay. All right. So now we're just gonna do quickly just a few example here, just to make a point of Steve Jobs' salary here in terms of Z-score. So this saying that when Steve Jobs was chief executive officer or CEO of Apple, he earned an annual salary of $1, and the CEOs of the 50 largest U.S. companies has a mean salaries of 1,449,779, and the standard deviation of 527,000. We want to convert Steve Jobs' salary to a Z-score and determine if it is unusual or usual. So yeah, this is actually true. At one point, he was earning annual salary of $1, and compared to the rest of the top 50 largest U.S. company, their CEO's mean salary is quite up there. So let's convert to, so given X, okay, so let's say X bar, okay, 1449779, okay, standard deviation. Notice I'm using the sample notation because it's referring to the top 50 company CEO. So now I say convert X equal to $1 to Z-score. Okay, all right. let's go ahead. Z equal to x minus x bar over s. So that's 1 is x minus x bar is 1449779 divided by 527651. Okay, let's see what the z-score is. So we got negative 1449778 divided by 527651. All right, so that's negative 2.75. So yes, Steve Jobs' salary is unusual because his z-score, his salary z-score is greater than 2. Okay, one more example. I'm going to end this first video and I'll do another one. So this is saying that if your score on your next statistics test is converted to your z-score, which of the following z-score would you prefer? A -2, -1, 0, 1, or 2, and why? So if your score on your next statistics test is converted to z-score, and z-score represents the number of standard deviation above or below the mean for a given value x. So which of these score we prefer? Well, the positive z-score means your score will be way above the class average. The negative z-score means is below the class average. So you want to do well, so you will want to prefer your score to be positive, the highest positive z-score possible, which is the 2 in this case, right? So you want to say a z-score of 2 means that you it means that your stats exam score is far above the class mean by 2 standard deviation. So that's what you want. Okay, you don't want a negative one. All right, I'm going to go ahead and end this first video, and then I'll do another one for the rest of this chapter 2. We're going to talk about percentile, and yeah, percentile.